Hello, welcome you all for this new video session on the Holtzer's method. This is a numerical method to find the natural frequency of the system. Okay, let us start with a problem. We are discussing Holtzer's method. It is a numerical method to find the natural frequency of the system. Already we know that this is a 3 degree of freedom system. For this problem, from the Holtzer's method, we can find all the 3 natural frequency of the system. Okay, in this method we need to write a tabular column which has 9 columns. Okay, which for all the problems, the particulars, all the columns, it is fixed. First column, it is assumed frequency. Here we need to assume the frequency. Second column, it is positions. We need to write the position of all the masses from the free end. The mass which is at the free end, it is the first position. This mass second position, third position, and this fixed, it is the fourth position. It is considered as the fourth position. Position 1, position 2, position 3, position 4. Okay, in the second column we are mentioning the positions, okay, which is same for all the trials. Next, third column, it is masses 1, 2, 4, infinity. Okay, for this problem, the mass at the first position, it is m. Okay, for this problem, m is equal to 1 kg. So it is 1, 2m, 2 into 1, it is 2, 4 into 1, it is 4, and it is a fixed end. So the masses are 1, 2, 4. The 1, 2, 4. There is no mass at the fourth position, so it is written here like this fashion. Okay, this mass for all the trials, you have to write the same masses 1, 2, 4, infinity, 1, 2, 4 for all the trials. Next, displacement. In the displacement column, we are assuming the displacement, first displacement, it is we are writing as 1. Next, this in the next fifth column, it is inertia force. We are calculating inertia force by mi omega square xi. What is m? It is the mass. What is omega? It is mentioned in the first column, that is omega equal to 0.1, and xi is the assumed displacement, it is 1 here. Okay, mass, this one we are considering from the free end 1, 2, 4, infinity. So we are taking 1, 2, 4, infinity, and this displacement, it is assumed displacement. It is you always take 1 in the first trial. First displacement, it is always 1. Next, you find the inertia force by mass, frequency, and displacement. This is the mass 1 into omega 0.1 into displacement. It is displacement 1. Okay, so 0.01. Now at this time we know only one inertia force, that is 0.01. You write the same inertia force here, and in the 7th column you are writing the stiffness values. It is also from the free end 1, 1, 3. See here, stiffness value, it is k, k is equal to 1 Newton per meter. So it is 1, 1, it is 3. So in all the trials we are writing 1, 1, 3. It is 1, 1, 3. Now at this time we know only one inertia force, summation of inertia force. It is summation of inertia force, it is 6th column divided by 1 by k, that is 7th column. Okay, 6th column value divided by 7th column, that is the 8th column value. Okay, now in the 9th column value we are subtracting this 8th column value by the 7th column. So 1 minus 0.01, it is 0.99. Okay, this is considered as the deflection for the next mass 0.99. This 0.99 you have to take here. Okay, you repeat the same thing. Okay, this is already taken, masses, it is already taken. Now the displacement, it is carried forward by this value. Now now you find the inertia force. Mass is 2, omega square, it is omega square, it is 0.01 into displacement, it is 0.99. So now you have this inertia force. At this time you have two inertia forces, 0.01 and 0.019. So you sum these two values, that is 0.0298. now it is already taken. It is this value, 6th column divided by 7th column, 0.0298. so this minus 0.0298, it gives you 0.96. this is the deformation for the next one, 0.96. you repeat the same thing. So this is the displacement. You take it forward. This is the displacement value from the first trial. Now you increase the omega value for the 0.2. Omega square, it is 0.04. okay, you take all the positions, you take the masses, it is same. Now you assume the displacement. Okay, the calculation part, it is same for all the trials. Okay, by taking different frequency, for different frequency, for 0.2 you will get 0.76, for 0.4 you will get 0.18. You are repeating all these steps until you will get 3 times there should be change in the sign. Okay, what it does mean? See here, this for this frequency, it is displacement value is positive. Okay, for this displacement it is again positive, there is no change in the sign. For this displacement the displacement is again positive, there is no change in the sign. Okay, for 0.5 the displacement is, there is negative sign. Okay, see here, in the previous trial it is positive, now it is negative value. One time there is change in the sign. Okay, for 3-degree freedom of system you have to repeat until you will get 3 times there should be change in the sign. Here 0.182 minus 0.1, one time there is change in the sign. Okay, from negative, if there is sign change, in the next case minus to plus, then 2 times, but in the next step again it is negative, it is 0 means it is change in the sign. So 2 times there is change in the sign. For 3-degree freedom of system, minimum we need 3 times sign to be changed. This is a positive value. Again in the next trial it is positive value. Okay, now for this trial it is negative. So 3 times we get the sign changes. For 3-degree freedom of system, at least we need sign change 3 times. Okay, you assume this frequency by calculating omega equal to square root of k by m, where k is equivalent spring stiffness. That is, for we have 3 spring stiffness values, 1 by ke equal to 1 by k plus 1 by k plus 1 by 3k. You calculate this ke value, and omega equal to square root of k by m. This ke you will get from this equivalent spring stiffness, and mass, it is sum of all the masses, 4 plus 2 plus 1, it is 7. So it is 0.247. 0.247 you assume 0.1 or 0.15 or a 0.2. Okay, any value. Okay, but in this range you can also take 0.25, 0.5, like that. Okay, in this problem it is taken 0.1, 0.2, 0.4. Okay, now we have frequency values in the first column, and for these frequencies we have calculated the displacement values. For 0.1 it is 0.93, for 0.2 it is 0.76. Okay, taking this in the graph, in the x-axis it is x-axis we are plotting the, it is frequency values, and in the y-axis we have taken the displacement values. Okay, for 0.1 it is 0.93, for 0.2 it is 0.76, for 0.2 it is 0.76. Okay, taking all the points and joining. Okay, what the curve crosses this horizontal line, these points are the natural frequency of the system. So the curve crossing the horizontal line, origin line, it is the natural frequency. These are the 3 natural frequencies of the system. Okay, this is the Holtzer method. Okay, thank you very much.